Hello everyone, my name is Ritwik Giri, and today I'll be presenting our paper at DCASE Workshop 2020 on group must autoencoder based density estimator for audio anomaly detection. This is a joint work with my colleagues at Amazon Web Services, Fangzhou, Karim, Srikanth, Umut, and Arvindh. So this is the overview of my talk. So the problem we are trying to solve is audio anomaly detection problem. So I will introduce the problem, and it's an unsupervised setting. I'll explain why is it unsupervised. Next, I'll talk about the approach, the way we solve this. So essentially, we're introducing a neural density estimator in this paper, and we use that group must autoencoder, which is an autoregressive model for density estimation to solve this. The key idea is the autoregressive decomposition of the joint distribution as conditionals over groups. Why is it useful? Because it can be used to represent a sequence of STFT frames or male spectrogram frames in audio. Let's talk about the unsupervised audio anomaly detection problem for a bit. So why is it unsupervised? Because we assume that the only data available to us for training is normal operation data. That means there is no anomalous data point available to us for training. So we cannot solve it as a supervised classification problem. Popular approaches to do this is one approach is solving it using an autoencoder based approach, where you train a vanilla autoencoder using all your normal training data. And during inference, if your model struggles to reconstruct the input, it basically means that it's sampled out of your distribution. So it won't be able to reconstruct that input too well. So you can just threshold on the reconstruction error and determine if it's a normal data point or anomalous data point. The other popular approach is a density estimation based approach. For example, here I show you on your left, if you see the plot. So for example, in this case, y is equal to 0 means normal data points. So all the normal data points is this distribution, the maze representation here. And what you can do, you can fit a distribution over all your normal data. And during inference, you can look at the log likelihood score. If it has a high log likelihood score, that means that you're doing inference, it's a normal data point. But if you see a low log likelihood score, you'll know that that's an anomalous data point. We are familiar with many popular density estimator, for example, Gaussian mixture model, where we solve a maximum likelihood problem to estimate the parameters of our Gaussian mixture model. Recently, neural density estimators have become really popular. And the idea here is that we can choose a parametric distribution p theta, but that parametric distribution can be a neural network now. And the design of the neural network has a couple of constraints because it needs to output a distribution. So it has to be a valid probability distribution. So if you integrate it over all x, it has to sum up to 1. Also, it has to be positive or non-negative. There are primarily two broad classes of neural density estimators. One is the autoregressive model approach, that's focus of our work, and then there is flow-based model, normalized flow, and many more. So I'll only talk about the autoregressive model part here. So as you know, autoregressive model basically means that if we have, let's say your input vector is x, which is say d-dimensional, you can take the joint distribution p theta x, and you can decompose that in an autoregressive manner. So if you look on the right-hand side, it's essentially the conditional distributions are xi, condition on all the other dimensions that have come before. So it's a product, and because it's a log, that's why you can see a summation here. And in neural density estimations, what you can do, you can represent this each conditional distribution by a neural network. You can model that as a neural network. So one of the earlier autoregressive neural density estimator is must autoencoder. It came out, I think, in 2015. It's known also as MADE, a short form. So the nice thing about this is that it shows you that how a simple autoencoder can also be used as an autoregressive density estimator. So what we all need to do is we need to make sure that each output unit is an estimated conditional distribution. So if we make sure of that, we can just multiply each conditional distribution to get our joint density. Remember, in autoregressive model, you basically have to make sure that, for example, in this picture, for node number 2, it's essentially the conditional of distribution of x3 given x2. So for this case, let's say the ordering that we're looking for, the autoregressive ordering, is x2, x3, and x1. So that's why x2 doesn't depend on anything, x3 depends on x2, and x1 depends on x2 and x3. So to use a simple autoencoder as a density estimator, we have to make sure that there is no path from this x3 output unit to, let's say, x1 or x3. Because to make sure that this only depends on x2 input, we have to make sure there is no path tracking back from here to either x1 or x3. Similarly, as you can see, because the ordering starts with x2, that's why the output distribution here, the conditional distribution of x2, does not depend on any of the input. So now to achieve this, all we have to do, we design corresponding masks and multiply the weight matrix to those masks to make sure that there is no path that we don't want. So for a feed-forward network, essentially you have a weight matrix, you just multiply, you zero out the connections that you don't want, and you can get the autoregressive ordering in that way. So that's why, as you can see, a simple autoencoder just by element-wise multiplied with this mask becomes a tractable autoregressive density estimator. So in our case, we adapt that to make it a group masked autoencoder. So the motivation behind that was because in this problem, we operate in log-mel spectrogram feature space. So let's say our input is T concatenated frames, and each frame has M mel bins. So what we want, so basically your input dimension is T multiplied by M now. But what we want though, we don't want autoregressive ordering in each dimension. What we want the autoregressive ordering across frames. So that's why we came up with this group masking. So what the group mask does, that it makes sure that when you are decomposing this joint distribution, it's a frame level decomposition. So essentially, if you look at this equation here, the joint distribution is decomposed as ith frame condition on all the frames that have come before. So essentially all the male bins in my ith frame, they depend on all the male bins of all the frames that have come before, but not any of the male bins that's in the ith frame or after that. So the difference between this and MADE is now we are decomposing that in a group structure. So in MADE, you'll have TI just as one scalar unit, but now TI is a group. So that's why we call it group MADE. There are two different models. So group MADE-G is basically where the output conditional is Gaussian. So essentially your autoencoder outputs the mean and variance for each conditional. And group MADE-MOG, the group MADE-MOG is where each conditional is a mixture of C Gaussians. So autoencoder outputs mean, variance, and the mixture component probabilities for all of the C components. Obviously, group MADE-G is a special case when C is equal to 1. For our experiments, we use C is equal to 10. So to give you an idea now, for a D-dimensional input, the number of outputs is D multiplied by C by 3. Because remember, each output unit is one conditional distribution, and that conditional distribution is essentially a mixture of Gaussian. So to represent that, there are C components per conditional. So that's why D multiplied by C. And for each Gaussian mixture, you need to have the component probability, the mean, and the variance. That's why the number of outputs will be D multiplied by C by 3. So till now, I have talked about only the causal ordering, right? But you can choose any ordering you want when you're decomposing the joint distribution, because that only changes how you're devising the masks. So for example, we use 3 orderings in our work. So ordering 1 is motivated from a recent work that came out at ICASE 2020. It's called Interpolating Deep Neural Network, where the idea was that if we have 5 frames, I'll use the first 2 frames and the last 2 frames to predict the middle frame. That's why it's called Interpolating Deep Neural Network. So what we can do is in our group MADE framework, we can just decompose this distribution T, which is basically of 5 frames, as two terms here. So there are essentially 2 groups. The first groups are the 4 frames, T1, T2, T4, T5, and the other one is basically just T3. So T3 condition on all those 4 frames is our other term. So essentially it predicts the middle frame condition on rest of the 4 frames. You can view that as like a probabilistic counterpart of IDNN. The second ordering is the standard forward autoregressive ordering, as I mentioned before. And the third one is also backward AR ordering. So it just, if you just switch the forward AR, it becomes the backward AR. So it starts from the 5th frame and goes back to 1st frame. So we also do an ensembling of all these 3 orderings. So we train GroupMate for ordering 1, for ordering 2, for ordering 3, and then we ensemble these 3 models to get our results. So the dataset that we use for this paper is the development dataset of DCASE 2020 challenge, task 2. So NTT and Hitachi organized a challenge for unsupervised detection of anomalous sounds for machine condition monitoring. There were 6 different machines in the challenge dataset: toy car, toy conveyor, valve, fan, pump, and slide rail. So they provided 10-second input files, and each file either came from a normal machine or an abnormal machine. For training purposes, we were only given the normal data points, and during inference, we were given some normal and some anomalous, and we had to make a decision if it's a normal or an anomalous data point. So on the feature side, what we did, we split all those 10-second input files into frames of 64 millisecond with 32 millisecond hop. We used 1024.FFT, and we also featureized each frame by 128 millbins. Finally, we use log millburn energies as our feature space. And as I mentioned before, 5 frames were concatenated. So that results into 640 dimensional input, because 5 frames and each frame is 128 dimensionals because of 128 millbins. The way the anomaly score happens is essentially for each input means 5 frames, we get a log likelihood from our trained GroupMate model. We take negative of that, and that's our anomaly score. So higher anomaly score means it's an anomalous point. Then we average all the anomaly scores that we get for each file. And that's how we get for each file, we get 1 anomaly score. To ensemble across multiple GroupMate orderings, 3 types of ordering that I just mentioned, what we do, we basically transform all the anomaly scores into a standardized scale, and we do either mean or max ensembling. I'll show you results using both mean and max ensembling. So here are the results. I know this is slightly dense, but the key things to notice here is essentially we compare with 2 models. Baseline was like a baseline feed forward autoencoder provided by the challenge organizers, and IDNN is the interpolating deep neural network paper that I talked about. And then, as I said, GroupMate G and GroupMate MOG, and 3 different orderings. And we also present the results for mean ensemble and the max ensemble. So other than I'm not going to go over all the numbers here, but the key thing to notice here that we see for valve, there's a huge performance gain from over baseline. So baseline was 66.28%. And these are numbers of area under curve. And as you can see for GroupMate G with mean ensemble, it went up to 95.60. Similarly, we saw significant gain for slider. We saw gain from all of the machines, but most of the gain came for slider and valve. So here's a nice picture that I wanted to talk about. So what I'm showing you here is on the left, it's for an anomalous valve. This is 1 recording. So this is the MEL spectrogram, and here is the anomaly score. B is the anomaly score that was generated from a baseline autoencoder, and C is the anomaly score that we got from GroupMate MOG. So the interesting part, as you can see, that for this anomalous data point, if you look at the anomaly scores, it's really high. So our model GroupMate is basically recognizing that it's an anomalous data point compared to baseline. Similarly, for normal data points, so this is a normal recording, you can see that even if you look at the scale, you can see that both the baseline and GroupMate, the anomaly scores are reasonable. It's not too high. So if you just threshold them, you can tell that it's a normal data point. The key thing here to see is for the baseline, you can see for both normal and anomalous data point, the range of the anomaly scores are very close to each other. While as for GroupMate, it's definitely picking up the anomalous data points well by giving a really high anomaly score. Finally, to conclude my talk, what we did in this work, it's a density estimator, group masked autoencoder for audio anomaly detection. We showed that it's a simple autoencoder that can be transformed to a tractable autoregressive neural density estimator. And by introducing this group masking thing, what you can do, you can basically choose your own ordering and design your group mask and That's what we showed in our work, that we also experiment with 3 different orderings, and if for the physical system you need a different ordering, you can implement that too. We also showed that interpolating deep neural network is essentially a special case of our framework. To finish this talk, this system was actually part of our ensemble system that we submitted to DCASE challenge, and it won the challenge task 2. You can go to the challenge task 2 results website to see more details. Thank you.